In our previous video, we focused on addition and subtraction with decimals, and now we're going to be doing multiplication. So um, we'll start with some visuals, some models. So these should look familiar to you. Uh, what we're thinking about here regarding multiplication is that conceptually, it means repeated addition. That's one way that we think about multiplication. 2 times 7/10, 2 times 7/10 means we take the value 7/10 shown here and we add it to itself twice. So we have it here and there. We line them up slightly offset in this visual here so we can see that this is where we end up with one whole square. So from here, this is 1, and then there's some left over here, 1, 2, 3, 4. Each of those columns is measuring a tenth. So 1 whole square plus 4/10 gives us 1.4 or 4/10. That was where we had a whole number times a decimal number, but many times we are multiplying decimal numbers times decimal numbers. So consider this: 2/10 times 3/10. One way this can be interpreted is 2/10 of 3/10. We use this when we were working with fractions multiplication. We thought about it as 2/10 of 3/10. Sometimes that word of helps us recognize what to do or how we might model it specifically. And so here is what a model of this might look like. What we'll see across the bottom here is our 3/10. 3/10 would be these 3 vertical columns, 3/10, each column representing 1/10. And then horizontally, we are then taking 2/10 of those. So each one of these horizontal columns is representing 2/10. So we're looking at where that overlap is between 2/10 and 3/10. And what does that realize then? It is 6/100. If I erase the little shading that I did, you can count them, right? You can see that those squares, 1, 2, 3, 4, 5, 6, all represent a hundredth. And so 2/10 of 3/10 is 6/100. So we like to start with that modeling so we can start to make sense of the again, the diagram, the illustration that shows how we are computing products. We often are computing them as if they are whole numbers, and then we locate the decimal point appropriately. So models work great sometimes when we're working with small numbers or easy to compute numbers, but not always when we're doing something like this. 27 and 48/100 times 9 and 2/10. So we're going to jump now to what our paper and pencil algorithm looks like, the traditional model. And it looks like this. I will do it over here. I will write my 27.48 like that, and then times 9.2. This is how we often line these up. And the first thing you might even notice is that those decimal points are not lined up. With multiplication, they do not need to be. And I'm going to explain in a moment why they don't need to be. You don't need to worry about lining up place values when you're doing this multiplication algorithm. So let's work through it. We start with the 2, and then we're going to multiply by each number consecutively, carrying and regrouping when we need to. 2 times 8 is 16. There's the 6, carry the 1. 2 times 4 is 8, plus 1 is 9. 2 times 7 is 14. There's the 4, carry the 1. 2 times 2 is 4, plus 1 is 5. Go down to the next level. Sometimes we like to put a 0 there. The key is because we're multiplying by this 9, our first digit will go right beneath it at that next level. 9 times 8 is 72. There's the 2. Carry the 7. 9 times 4 is 36. Plus 7 is 43. There's the 3. Carry the 4. 9 times 7 is 63. Plus 4 is 67. There's the 7. Carry the 6. 9 times 2 is 18. Plus 6 is 24. And then we add 6 plus 0 is 6. 9 plus 2 is 11. There's the 1. Carry the 1. 1 plus 4 plus 3 is 8. 5 plus 7 is 12. There's the 2. Carry the 1. 1 plus 4 is 5. And 2 plus nothing is 2. So we have a pretty big number right there. Now, the next piece is deciding where does our decimal point go. There are different ways to consider this. The most traditional way is you look at the numbers that you started with and you identify how many decimal places did you have in total in the numbers you multiplied. 4 was one of our decimal point numbers, and so was 8, and so was 2. So we had a total of 1, 2, 3 numbers that were in decimal places. You need to have that many in your answer. So starting from the right, we count 1, 2, 3. Those 3 numbers need to be in the decimal places, so we put our decimal point right there. Before you finish up, I always recommend you go back to your original numbers and you make sure your answer makes sense. We'll talk about approximations later, but for now, if you just look at 27.48 and 9.2, this is pretty close to 27 times 10. You know your answer has to be somewhere around 270, maybe a little less. This answer makes sense. It would not make sense for your decimal point to be here, making it 25, or here, making it 2,528. Based on the numbers you're multiplying, always make sure that your answer seems reasonable to get those decimal points in the proper locations. So now what I'll do is I'm going to just reference this same problem again, but I'm going to show it in another way with fractions so we can see how they're connected and also why that decimal point goes where I said it has to go. So we can consider 9.2 times 27.48 as this. 92 tenths, because this is in the tenths place, times 2,748 hundredths, because this is in the hundredths place. We discussed those things in previous videos in the earlier sections. When we multiply fractions, you remember that we multiply the numerators and we multiply the denominators. That would give us 1,000 in our denominator, 10 times 100. And this is a pretty big number, but it is 252,816. Now, that should help you start to see what's happening here. If we now want to rewrite this as a decimal, because our denominator is 1,000, we know that our last digit has to go in the thousandths place, 252,816. The only way to get that 6 in the thousandths place is to put the decimal point right there. 1, 2, 3, tenths, hundredths, thousandths. So this model links it to the traditional multiplication of decimals model, that traditional algorithm. So go ahead and we're going to have you try 3 different multiplication problems. They are as follows. 3.7 times 2.5, 4.6 times 0.35, and 1.8 times 0.473. Take a few moments to pause and work those out. So with this first one, I'm just going to paste what our multiplication algorithm would look like, it would look like this. Again, we stack the numbers, we multiply, check to make sure that your numbers matched what I have here. Once we get those two partial products, we add and we get 925. And because we had two decimal places in our problem, we're going to have two decimal places in our answer, 9.25. The next one is going to look like this. 0.35 times 4.6. Now, maybe you had these in the other order. It doesn't really matter what order you put them in. You should end up with these partial products, and when you add them, you get 1610. When you look at the original problem, we had two decimal places here, one here. That's a total of 3. So we need 3 in our answer, 1, 2, 3. Now, maybe you even rewrote it as 1.61, 1 in 61 hundredths. That's the same value as 1 in 610 thousandths. Either one would be fine. For the last one, it's going to look like this. When you get done with this and add your partial products, we had 1, 2, 3, 4 decimal places in our problem, 1, 2, 3, 4 in our answer. So that's some practice for you, some good practice for that multiplication algorithm when you have to do things by paper and pencil. So we're going to move on now to different multiplication models, right? What are these going to look like? How can we visualize them? We saw that earlier with our base 10 grid. We're going to come back to these. And so we're going to examine this problem next. 2.3 times 1.7. And if you remember back to our base 10 grids, we can start with a square, and we divide that up into 10 sections this way, 10 sections that way, which is 100. Those are all talking about those hundredths now. And we can model a problem like this the same way. We can stack two of these on top of themselves to be the 2. Again, this is just a very rough sketch, you can see. And then we go 0.3, right? So we would go 3 more tenths this way. Okay. And then 1.7. So this is the 2.3 on this edge. I'm going to make a nice, neat one, I promise you. And then we go 1.7 across the top. We already have 1 here, so we'd have to go another 0.7 this way. So we'd extend these, and this would be 0.7. So we'd have look like when it's all said and done, and I just closed everything on my computer. Here's what that's going to look like when we make it nice and neat. That's much prettier than my diagram. So let's take a moment to analyze this. So again, the number 2.3 we can represent this way. 2 and 3/10. Horizontally, it's 1 and 7/10. And when we multiply those, we are calculating the area of the space that's filled in here. And so 1.7 times 2.3, this is a total of 391, when it's all said and done, of these individual hundredths squares. 17 times 23 is 391. But because we were working with decimals, we know that that 1 is going to be in the hundredths place because we were counting squares, each one of them representing hundredths. So one of the content standards for the National Council for Teachers of Mathematics talks about numbers and operations, and we're going to explore this one. It says multiplying, dividing fractions and decimals can be challenging for many students because of problems that are primarily conceptual rather than procedural. Again, procedural, you are following steps and rules and algorithms. It's so crucial to have that conceptual understanding at the foundational level. From their experience with whole numbers, many students appear to develop this belief, a false belief, that, quote, multiplication makes bigger and division makes smaller. So I'm just curious for you to analyze your own thoughts. Consider this statement. Multiplication makes bigger and division makes smaller. Is that something that feels like a correct statement to you? Or does something in your brain say, I'm going to challenge that statement? What I'm going to have you do now is this little activity. So, sketching out a base 10 grid diagram, kind of like we did earlier, right up here. So just sketch something very, very brief that looks like this to show that the product of two decimals, each between 0 and 1, so the decimal numbers that are between 0 and 1, is less than either of the decimals in the product. So we're going to use 7/10 times 8/10. So see if you can do that. Multiply 7/10 times 8/10 using a diagram. It can be very rough. It doesn't have to be perfect. But we're working on developing this idea, challenging this highlighted statement right there. So take a moment to do that, please. What you might have created is something that looks like this. This was mine. Again, I did mine in Microsoft Word, made a little table and shaded some things in. And so what we have here, again, is a value of 1, right? This is a block of 1, and it has tenths going across, tenths going down. So each one of these squares represents a hundredth. Across the top, this is 0.8, 8/10, right? If we look at all 8 of these columns. Across the side, we have 7/10, all 7 of these columns. When we multiply those two things together, we are only looking at these purple squares here in the middle. And if we count them, it's going to be 56. 8 times 7 is 56. So this purple section is 0.56, which is 56 hundredths. 56 hundredths is less than 8/10. Let me be consistent and not use the decimal. 8/10. 56 hundredths is less than 8/10. 56 hundredths is also less than 7/10. So the product of two decimals between 0 and 1 is less than either of the decimals in the product. What we got as a result was less than both of the numbers that we started with. And that is something that is challenging for many students to comprehend because of this notion, their experience with whole numbers. They assume that anytime you multiply anything, the answer gets bigger. And anytime you divide by anything, the answer gets smaller. But we can see here that that is not always the case. And so showing that with these models is a good way to do that. So the last thing we're going to talk about in this video is when we multiply by powers of 10. And one way to illustrate this is using decimal squares and this idea of repeated addition. And so before we even do this, I'm going to show something that many of you probably already know, or maybe have forgotten, but you saw it at one point. 10 times 1.65. Nope, sorry, wrong thing. 10 times 0.165. When you are multiplying by the number 10, you may have been taught at one point is that that slides your decimal one place to the right, giving you 1.65. So that might be something that looks familiar to you. If not, that's okay. What we're going to be focusing on is why, right? Why this works the way it does. And so that starts with analyzing some pictures. So I'm going to pull in this picture and we're going to take a few minutes to analyze what's going on here. So on the left, notice what this picture represents, this upper left-hand corner. This represents 1/10, 0.1, okay? And we are going to multiply that by 10. So 1/10, when we multiply it by 10, would fill in all of those columns, giving us one entire square. So 10 times 1/10 is equal to 1. Now let's look at the next picture. In the middle on top, 0.01 is 1/100th. Multiply that by 10, and it fills in that entire first column, which is equal to 1/10 or 0.1. So 10 times 100th is 1/10. 10 of these makes one of these. Now let's go to the next diagram. 0.001, 1,000th. When we multiply it by 10, it's going to fill in this entire little square right there, which is 100th. So 10 times 1,000th is 100th. So did you notice there that every time we multiply by 10, our 1 gets shifted one place value to the left? So that's an important thing to recognize. And this is why, right? The diagram is why. So now I'm going to take this problem that I showed you right here, and I'm going to illustrate it using this concept that we just discussed. So if we look at the starting value of 0.165, 165 thousandths, this is what it would look like. But what we're then going to do is take this and we're going to multiply it by 10. And we will do it place value by place value. If we just look at the 0.1, the 1/10, that's this column here on the left. So here is our 1/10. If we multiply that by 10, it turns into one full square, the number 1. Then we go to the 6, which is in the hundredths place. Well, that's this amount right here. 6/10 takes us to there. If we multiply that by 10, then we have, 6/100ths, I said tenths, 6/100ths. If we multiply 6/100ths, they turn into 6/10ths, which you can see here. And then we go to this last section, the 5 thousandths, which is shown there. If we multiply that by 10, those 5 thousandths turn into 5 hundredths. Each of those digits shifts one place value to its left. And so when you multiply 10 by 165 thousandths, you get 1 and 65 hundredths. Rather than imagining the decimal moving, I think it's even better if we imagine each of the numbers themselves moving one spot to the left. It essentially has the same effect, but I think conceptually it tells the story a little bit better when we're multiplying by that 10. Another way we can show it, as we've done before, is connecting it to the idea of fractions. And here's what that would look like. 10 times 0.165, if we separate each of those place values into their fractions, the 0.1 would be 1/10, the 6 would be 6/100ths, and the 5 would be 5 thousandths. When we multiply this by 10 and distribute that 10, what we have is, instead of 1/10, we now have 10. Instead of 6 hundredths, we now have 60 hundredths. And instead of 5 thousandths, we have 50 thousandths. Simplifying or reducing each of those fractions, we now have 10 tenths, which is 1, 60 100ths is 6 tenths, and 50 thousandths is 5 hundredths. Put those back in their decimal form, 1 and 65 thousandths. So you can see all of these different ways to view this problem, multiplying by powers of 10. If we condense it into an algorithm, to multiply by a decimal by a power of 10, move the decimal point one place to the right for each power of 10. We just spent a lot of time talking about how to move the decimal point when you're multiplying by the number 10. But you move the decimal one place for each power of 10. Meaning, if you're multiplying by 10, you move the decimal point one place to the right. If you're multiplying by 100, well, that is 10 to the second power. So you would move the decimal point two places to the right. If you're multiplying by 1,000, which is 10 to the third, you would move that decimal point three places to the right, and so on. So let's finish this video with a couple of these for you to try. So we will try 100 times 0.45. We will try 10 times 14.08. And we will try 1,000 times 0.32714. Take a moment and try both of those, or all three of those. For number 1, we were multiplying by 100, so we will shift our decimal point two places to the right. There's 1, there's 2, and we end up with 45. Our decimal point is all the way on the right, so that's just the number 45. In number 2, we're multiplying by 10, so we move our decimal point one place to the right. That jumps the 0. 140.8. 140.8. 140 and 8 tenths. On number 3, we have 3 zeros, and so we'll move that decimal point 3 places to the right. Jump 3, jump the 2, jump the 7, and we have 327 and 14 hundredths. Now, one final thing that I didn't know before. If we are multiplying 100 times 17.2, we move our decimal point, because the number 100 is 10 to the second, we would move that two places to the right. We jump the 2. If there's not a number there, you know that there is a 0. So in this case, it would be 1,720. That is multiplication with decimals. In the next video, we will work on division.